Okay, so good morning, everyone. Let's get started. So the first talk would be by Haruki Watanabe from University of Tokyo, and he would be talking about frustration-free quantum many-body systems and their applications.
Great, thank you so much. First of all, thank you so much for inviting me for this wonderful, not really workshop or conference, right? It's like a very interesting meeting, and I'm very happy to be here. Then I'm going to talk about, let me start by defining what I mean by frustration-free systems. So the Hamiltonian is frustration-free if I find some decomposition and each local Hamiltonian is finite ranged, and if this GS is a ground state of the total Hamiltonian, then GS is a ground state of each local Hamiltonian. So let me explain. So supposing like I have Hamiltonian term H1, H2, and so on, right? In order to realize the ground state of this total Hamiltonian, sometimes by minimizing this local term H1, I need to pay some cost. Maybe the energy of this term H2 will be increased, right? So there might be some tension or frustration between achieving the minimum of this total Hamiltonian. But today, I'm going to focus on some special class of Hamiltonian, which is called frustration-free, because each local terms can be simultaneously localized, minimized. Okay, so that's the kind of definition of frustration freeness. So So this is a very special property of this, defining property of this frustration class of Hamiltonian. But these local Hamiltonian terms do not have to commute. So when they commute, we know that they can be simultaneously diagonalized, and you can achieve the simultaneous minimum. But even when they do not commute, you can sometimes achieve this simultaneous minimization. Okay, let me give you an example. So toric code model we have heard several times. This is commuting project Hamiltonian. So toric code model, bracket term and vertex terms all commute. So this is a simple case. But for example, like AKLT speed chain, SI plus 1, vector, SI plus SI plus 1, vector squared. Okay, so this model, it is known that this is frustration free. And for this model, each local term do not commute. But in the ground state, you have ground state is simultaneously a ground state of each local term. So what I'm saying here is that in general, the general quantum many-body systems, you have like a subclasses, right? Like this is a frustration-free subclass, and this is like, for example, commuting projector. So if Hamiltonian is this kind of commuting projector type, usually you can simultaneously minimize all terms, and usually there's no obstruction to achieve the absolute minimum of each local term. But you might notice that sometimes for example, if I said plus here, you need to realize minus of these local terms, and sometimes it is very kind of like a global constraint that is that plays a lot of obstruction to achieve the absolute minimum. But okay, I'm not talking about such kind of thing here. So usually, like commuting project Hamiltonians are also frustration free. So which is subclass of these frustration free models. Okay. And so what do we know in general about these models? Is oh yeah, yes, thanks. Yeah. But I will give you an example which is not the sum of projectors. Yeah. Yes. Yeah, that's what I was saying, Oh. Uh-huh. I think the meaning of the frustration is kind of different then, like uh-huh. So you're saying it's actually rare. But is it different from this kind of like a toric code model with opposite sign? Toric code with opposite. Oh, okay. Yeah, you might be correct, but it's not really like a. Okay, so I'm saying then maybe I need to say like maybe like this. Some of the commuting project Hamiltonian. Yeah. Okay. This is fine. Yeah. But so okay. So some good commuting project Hamiltonians here, bad commuting project, more non-trivial commuting project Hamiltonians there. Okay, great. Thanks. Yeah, and also like I forgot to ask you to ask more questions, right? Like I think this is Blackboard talk, and the whole point of this kind of Blackboard talk is to be more interactive. So I want to really proceed maybe on the same page and very slowly. So yeah. No. So that's really important. Thanks for asking. Like I will also discuss that exponential tail is at the end, like this is all about definition. So this is my definition, and it is your freedom to include exponential tail, right? But I will discuss that this definition is more useful than the more physical definition that includes an exponential tail. All right. So then, like, what do we know about this? Subclasses, right? So commuting projector Hamiltonian, which is actually trivial class of commuting projector Hamiltonian that allows us to write down common ground states. Then we know this is in general gapped, right? Because in the ground state, this is projectors, and in the ground state, we know this belongs to say 0 of the this projection operator, and in the excitation, like some of this becomes +1 in the eigenstate basis. So excitation energy cost is always the multiple of integer, right? So this is gapped. On the other hand, in general, we know that the general quantum many-body system can be gapless, can be gapped or gapless. Yes. And if it is gapless, I want to understand how fast this energy level goes to 0. Okay. So my definition of gapped is that the energy difference of the ground state energy level to the one above. This difference is delta, and delta goes to a finite number, which is positive. This is called gapped in my talk, in the limit of thermodynamics, in the thermodynamic limit, right? And if this goes to 0, I want to call it gapless. Okay. In the gapless system, I'm interested in how fast this energy difference goes to 0 in the limit of system size goes to infinity. And okay, this definition might indicate that this is 1D, but it's not true. Like I'm interested in quantum energy system in any dimension. So you may call 1, 2, 3, 4, or you can assign a pair of label x, y. But anyway, like I have a label of each local term, and I'm interested in general quantum many-body systems, and this linear dimension of the system is L. Okay, so it might be Lx and Ly, but this typical length is this L. And usually this L is 1, right? In general, but it can be higher. But in general, typically this is 1. Like for example, if you have a gapless degree of freedom with linear dispersion, then the first available momentum is 2 pi over L. So if the dispersion is linear, then this is like this number, right? So typically, this exponent z is 1. Okay? So how this is different in translation-free subclass? So should I use only these two part, or can we go further there? Or okay. Yeah. Okay. So this is general class, and this is commuting projectors class. So if the Hamiltonian is translation-free, I want to say if it is gapless, delta is always so this is a claim for in general for translation-free class of the model. And if it is gapped, I want to talk about a topological property. So in any dimension. Yes. So the volume is L to the power D, typically. Yeah. You are allowed to have like different aspect ratio, but typically, volume is L to the power D. Any questions? Yes, exactly. Yeah, that's the point here. Yeah. And I think this is a kind of well-known property for each model. Like people have looked at many different types of fluctuation free model, like RK limit or the Diamond Hamiltonian, or like many classes. People have realized that in these models, particularly in the example, that for example, dispersion of the low excitation, low energy excitation goes like k squared. But I'm saying, this is a general property of fluctuation-free systems. And I'm going to kind of give you a partial proof of the property. In general, I think this is still not fully established yet. I have only a partial proof of it. Okay? And if gapped, I want to talk about topological property. This question. So here, for example, for commuting project Hamiltonian, we know such kind of distribution exists. For example, people realize that challenge later is not possible. Commuting project class Hamiltonian is always gapped, but so this is Kapustin, Fidovsky, Fidokov. So in general, we have challenge filters, but if you restrict too much, you cannot realize challenge filter. Then like you can ask, what if you relax the system to frustration-free subclass? Do we have challenge filters, right? And I'm saying, I think still it is absent. But still, I don't know that. So if it is quantum, so if it is, so suppose I have quantum many body systems with U1 symmetry, and I want to assume a gap between ground state and excitation state. Then if I have a gap, if I have so if it is like a non-interacting fermions, I define Chern number by integral dk, very curvature, and this Chern number, non-zero Chern number is a kind of definition of challenge later. If this is interacting fermion or interacting, interacting fermions, like I use the definition. I just replace this k by twisted boundary condition. But more general, I think you have a. You can. The question is how to characterize Chern number from wave function or ground state, like a commutation relation between projector and the position operator. There is such kind of formula as well. So you should use some formula to give you. Yes. Exactly, ground state is always what? Yeah, I think ultimately that is the reason. Yeah. Yeah, thanks. Yeah. So maybe you already know the proof of it. I don't have really a general proof of this claim. So I think no one have ever. Yeah. Yeah, maybe we can chat later. Yeah. I think I can learn a lot from you. So yeah, thanks. Yeah. All right. So anyway, so like you can use your favorite definition of Chan integrator, and I think it is the Chan number is always 0 for this fluctuation-free subclass as well, not only this subclass. And but more generally, I want to explore what kind of topological phases available in the general fluctuated systems. What is the limitation in this fluctuation-free subclass? So that is the question I'm asking. So classification of available topological phase. So these are what I'm going to discuss today. Okay. Maybe I can also use this one too. Okay. Yeah. So I'm going. I will discuss fluctuation-free free fermions, but I'm saying not all free fermions are fluctuation-free. Yeah. So there are some subclass of free fermions which is fluctuation-free. Yeah. So so let me start by partial proof of the so my assumption is that Hamiltonian is fluctuation free. Also, like there exists a correlation function of some operator some power. So if I can additionally assume the existence of operators such that their correlation function decays only power law, not exponentially, then I can prove that Z is greater than 2. So I'm saying this is a partial proof because this is an additional assumption, right? Okay. Yes. Sorry, G is a projector onto ground states. Ground states. So if you have multiple ground states, you need to include everything here. Yeah. Sorry, like maybe I should use the same notation here. So like this is GS. Yes. Is it okay? Yeah. And the proof of this discussion based on very nice work by Bosset. PRL. So in this paper, they derived a very nice bound of correlation function. So I need to give you a definition of these parameters, but these are just constants you can define based on this definition. So Hamiltonian. For example, this G is the number of local terms that does not commute with HI. So you have HI, right? There are terms that kind of neighboring terms that does not commute with this HI, right? So that is defined as GI, and the maximum number of GI is called G. Okay? That way, like like these are just constants. This epsilon, this quantity epsilon is an important quantity, and this is defined to be so basically this is a normalized gap. So this gap is appearing, something appearing here. Okay. And this is very surprising inequality because sorry, this is a distance between operator OX and OY. So if you use standard lattice distance, you can just say this is something like x minus y. Yeah, you should understand this x and y as a vector. Okay. Any questions? Yes. Yeah. Okay. So in this paper, they introduced a notion of interaction graph. So like I have interaction terms. I have a graph in which vertices are given by Hamiltonian terms, and I draw edges if they do not commute. Okay? So this gives you a graph, right? So I draw this edge when they do not commute, right? For this graph, I can talk about chromatic number in order to color them differently. Like this is yellow, this is blue, and if this is blue, and if this is connected, this cannot be yellow or blue, so this can be red, for example. That is the minimum number of colors to give different colors to neighboring vertices is called chromatic number, and this C is that number. But this is point is that this is finite. So these are finite, yeah, order one quantity, yeah. So for given decomposition, you can deduce these constants, and this is a general correlation bound for frustration-free systems. And I'm saying this is very surprising because in general, for example, Hastings PLL, he bounded almost the same quantity, but I think he usually uses operator norm here. Is bounded by some constant here, an exponential distance or x or y, and the Lip-Robinson velocity here, and yeah. So in general, so this is for frustration-free class. This is for general class. In general quantum many-body systems, Hastings derived very nice bound of correlation function. Sorry, like maybe you need here. And that is exponential decaying with distance, but you have this gap here, and you have Lip-Robinson velocity here. So this is usually people quote this result as an exponential decay of correlation function in gapped systems. But if you follow the calculation, this epsilon is just the energy difference between the ground state and the first excited state. So you can use it in gapped system as well. But I'm saying what is surprising in these two inequality is that you have additional factor of square root here. So this is really the key. You have question one? No, okay. Yes. Oh, I'm sorry. I'm so sorry. Yeah. So this is ground state. It's my bad. Sorry. Any other questions? Yeah. I'm working. I'm always working in a finite size system. All right. Here? No, I don't have a square root here. 2 v, 2 times v. This v is like some velocity. It's like a parameter appearing here. Yeah, yeah. Good. Okay. Yeah, so our argument goes like this. So we assumed the existence of the correlation function that decays like a power law, right? So this correlator so this correlation function decays with some power, but here I want to apply this result for an operator separated by for example, y minus x is half of the system size. So, for example, in two-dimensional model, I assume torus, and I set x to be here and y to be the opposite side of this ring. Then I can realize, this, y, the distance between y and x are half of the system size in x direction, right? So this is L to the power p. Okay. On one hand, this is what I have from the assumption. On the other hand, the same quantity is now bounded that way. So this is like a half of the system size, and the square root and epsilon g squared plus epsilon. So suppose this epsilon behaves like 1 over L to the power z, okay? Then if z is actually smaller than 2, then in the exponent, what I have is L to the power 1 minus half of z, which is positive. So this guy decays kind of exponentially. So this contradicts with this behavior. So just by using their result, actually, we can see that this is necessary to achieve a parallel decaying correlation function. Okay. So yeah, what is really non-trivial is already hidden in this correlation function that you can prove it quite generally using a technique called like a detectability lemma, and also very naive. This argument is pretty general, like they can prove it on an arbitrary graph, and the boundary condition is not really important for them. Okay, good. It can be anything seriously, like yeah, okay, so okay, then if you ask me that question, like let me give you one example. So let's talk about this model. So, okay. So usually, like people say U1 symmetry will not be broken in spatial dimension 1, but I found in translation-free systems this is sometimes possible, not always. So let me. Not SU2 symmetric. This is U1 symmetric. Yeah. Yes. Yeah. So I come to that point too. So let me explain. Let me write down the concrete Hamiltonian. So this is given as the sum of local terms, and the local terms is like this written this way. Sorry, this delta is not the delta I was using here. This is just a parameter. Should I use different character here, or is it okay? I think in this context, like a XXZ model, people pretty much use this delta right here. Sorry about that. Yes. Yeah. So yes. So if Hamiltonian is free, and if it is gapped, then the Hastings bound always apply, and it implies it is exponentially decaying. So this assumption implies that it is gapless. Then this kind of improved bound tells you that it is Z is greater than 2. Yeah, sorry, I'm going too slow. But I think like a 90-minute talk, you cannot really focus on the entire part of the talk, right? So I kind of personally prefer going slowly and. Yeah, so this is Schema model. Sorry, yeah, very good point. Yeah. I'm now looking at the spin chain and the periodic boundary condition, and this is my model. And when delta equal 1, this reduced to the Heisenberg model. And it has SU2 symmetry. And with this SU2 symmetry or SO3 symmetry, people have known very well that it shows kind of spontaneous symmetry breaking in any dimension, right? But I'm not talking about that. So I'm talking about the U1 symmetry of this model. which is just some of the decomposition of spin. And I want to talk about an order parameter, which is sum of I, Si, X. And then, what I do is the following. So what I do is to apply magnetic field. And compute ground state as a function of this external magnetic field. And I compute order parameter value. This is called, divided by L. And I take the limit L goes to infinity first, and B goes to 0 later, and see if this is 0 or non-zero. Okay? Yes. So I'm saying this is kind of counterexample to that rule. Say that again. What? Yeah, but right. So okay, so I'll come back to that point too. So here I will draw the argument, my argument. So let me just first explain my result. Okay. Yeah. So sorry, like okay, I need to specify that I'm working in t equals 0. Okay. I'm looking at the exact ground state available in a finite box under magnetic field. Okay. In this sense, so magnetic field in x direction, right? Good. So so this quantity as a function b, and that it really behaves like this. So if I approach from positive side, I got this positive number. If I approach from negative side, if I get negative magnetization, it looks like a higher dimensional case. Okay. So I found exponential symmetry breaking of U1 symmetry in 1 dimension for this spin chain. I was very surprised, and this Hamiltonian. Yeah, always order parameter. So like I'm applying magnetic field in x direction. It doesn't commute. That's the point. Yeah, that's a really important point. So yeah, so like this SU2 case, this order parameter and Hamiltonian commute. So there's no quantum fluctuation. The ground state can be taken as an eigenstate of this operator O, and nothing really surprising in this example. But here, what is crucial is that O and H doesn't commute. So I thought it's impossible, seriously. But so sorry, like let me give you a reference. Jong-Yon Lee and Katsura. I think I need to give you a reference for this one too. Masaoka, Soejima, Watanabe. But this is not the only result of this paper. I wanted to talk about that too, but Let me first finish this discussion. All right, so we find somehow a symmetry breaking in this model, but we also found that the excitation of the lowest energy mode is k-squared, just like in the ferromagnetic model. So although we have only U1 symmetry, and actually you can prove that this model does not have additional symmetries. It doesn't commute, does not commute, sorry, like it commute for delta equal 1 special point, but I'm saying for general delta non-zero, not equal to 1, although this doesn't commute, but it still shows this behavior. Yes. Yeah, that's a good point. And so I think like recently people try to prove that each given Hamiltonian is what is the name? Brand in Japan, like given H judge if it is integrable or not. And what they do is like it really like assumes a form of Q, and kind of they really solve this equation as a like a linear equation between coefficient. So Q is expanded in the series of the coefficient times possible operator basis, and they view this equation as a linear equation between these coefficients, and they discuss the existence of the solution. And I applied there. So this is like the Shira Shi at U Tokyo is initiated this program, and so far many models have proven to be non-integrable, and I think this model also falls into non-integrable classes, and you can kind of prove the non-existence of the conservative quantity of this type, like some spin operator at some point, and the spin operator at neighboring site, and this kind of spin strings and the sum. This form of quantity is not doesn't commute with this Hamiltonian. Good. Thanks for asking that question. Any other questions? Yes. Yeah. So maybe like you need to look at his paper. He's really expanding Q in the series of these like spin operators. In some basis, like say if in the spin model you need to expand it in the spin coefficient alpha beta I plus 2 gamma, right? And he discussed the existence or absence of say length 3 conservative quantity or length 4 conservative quantity, and he reduced the equation set in kind of proof by reduction. If the conservative quantity with length L exists, then L minus 1 exists or not, or that kind of proof. Yeah. Other questions? Yes. Right. Mm-hmm. Right. So yeah, I'm saying like this is, to me, this is the definition of spontaneous symmetry breaking, and it satisfies that. So like this is, you may call this like a spontaneous symmetry breaking of U1 symmetry. So the spin spontaneously choose one direction. It's like really the magnetization, right? But this magnetization is not a conservative quantity. Yeah, right. Yeah, that's really important. Yeah. Right. Oh yeah, okay. I looked only at vicinity of delta. So including one, this U1 symmetry breaking, and this is like a SU2 symmetry breaking, but Yeah, this is SU2 symmetric point. Yeah, having point. Yeah, exactly. Yes. I don't know the beyond that point. Yeah. I don't think people have done that yet. Yeah. Yeah, so so I have symmetry generator and some auxiliary field. The commutation relation is order parameter. And so let me kind of sketch the proof of Marmin-Wagner theorem. So let me introduce QK. Okay. So for example, in the spin model, this is Z component of spin, and this is X component of spin, and this is Y component of spin. Okay. And in general, like Marmin-Wagner theorem is proven by this inequality. Yeah, so it's kind of complicated. Sorry about that, but not that bad. So divided by good. So this inequality is called Bogoliubov inequality. And the proof of this Bogoliubov inequality is very simple. Like you need to use just a Schwartz inequality for some correlation function. I think I included the proof of this inequality in my paper. And the point is that this is like order one quantity. And in the numerator, what I have is the commutation relation between QK and the XK. So this is a kind of order parameter. So in the limit K goes to 0, this part goes to order parameter expectation value. So like let me call it M. So this is like a M monetization. Okay. Yes. V is the volume of the system. Sorry. Yeah. T. Sorry, this is temperature. Sorry about that. This is temperature. So originally, like Fermi-Magnus theorem is proven for higher temperature, and we are interpreting it in a lower dimension at 0 temperature. So I'm explaining the sketch. I'm sketching the proof of the original Fermi-Magnus theorem, and it is originally proven for the higher temperature. Any question? Yeah, okay. There's a separate discussion in high energy size, like a Coleman theorem, right? That assumes Lorentz symmetry. And here, I'm saying excitation spectrum is k squared. So it absolutely, violates Lorentz symmetry. So that kind of field theory argument doesn't work here. Yes. I am not sure about that. Yeah, good point. Yes. Because I wrote down the ground state. Actually, like data. So maybe. Okay, I plan to talk about fermions as well, but I think I can skip it. Yeah, let's focus on this bosonic discussion. And then, like, I can talk about. I can talk about the secret behind this model. Okay. So the Hamiltonian is now a sum of local terms, right? And suppose this is positive semi-definite. So then, like, you can always write it in this way, something like this. And the ground state is annihilated by this L. So this is a kind of structure of the Hamiltonian, right? And there's a very famous technique called Witten conjugation. So what this Witten conjugation does is that, you kind of start from simple Hamiltonian, and you generate prime here, and HI prime is Li dagger, Li, and you insert possibly some operator here, and M. I don't remember if I have dagger there or not. I think I have dagger here. Yeah. Not dagger. Yes. What I wanted to say is GS so GS prime is M inverse dagger. Oh yeah, I think this is correct, maybe. Yeah, the point is that, starting from some simple Hamiltonian, you can design a new. So suppose this is frustration free, like this is the definition of frustration freeness, right? Starting from this simple limit, you can always design a series of Hamiltonians, which is also frustration free for this reason. And this operator M is this is invertible, but not unitary. If this is unitary transformation, it doesn't change spectrum, it doesn't change symmetry. But if it is non-invertible, invertible but non-unitary symmetry, the symmetry might be different, spectrum might be different. And in this case, actually, this delta not equal to 1 limit, delta not equal to 1 model is connected to delta equal 1 model. So this is Heisenberg model. So there exists an invertible but not unitary operator that brings this famous Heisenberg model to our model. So that is actually the reason. Yeah. And I know it, there is a common ground state. Yes. Oh yeah, okay. You can just look at my paper, and I don't know what was that. Yeah. Yeah. Okay. Yeah. Okay. It's something. No, not here. Here. Yeah. Yeah. Sorry. Right. Because like if you take determinant of H prime, seems to be M and M inverse cancels. Oh, is that right? It must be Hermitian. So, okay. Yeah, okay. Thanks. Yeah, good. So that is why like I know that this model is classification free. Yeah. Yeah, it's arbitrary. So like I'm just talking about how to generate classification free models starting from some simple limit. And this can be already different classification model. But in my case, I needed to include this CI because I have a specific goal, right? Like I wanted to connect two Hamiltonian delta equal 1 and delta equal not equal to 1. That required me to include this local term CI. Yeah. Great, thanks. Yeah, there are some conditions. Yeah, sorry, it's not free general. Thanks.
The question online?
Yes.
So how do I see that this transformed Hamiltonian will also have a k-square dispersion?
Say that again.
How do I see that this transformed, this H prime also has a k-square dispersion?
No, you cannot see that. You cannot see it. Like transformed Hamiltonian and the original Hamiltonian have different dispersion. It is possible that one of the two Hamiltonians are gapped and the other one is gapless. Okay. This transformation can change even gapless or gapped property as well. So it can also change dispersion relation.
Okay.
It's not obvious. So we just did the simple single mode approximation to write down a variational state which gives you k-square dispersion.
Okay, thanks.
Good, thanks. Yeah, it's only this transformation really generates different classification free model. All right. Yeah. So so I was in the middle of the discussion about Mann-Wagner type theorem. So I think the original proof is proven. Our original theorem is proven for general non-zero temperature, and there is no exception to this rule. So I think in two-dimensional stat-mech model, I think there is no symmetry breaking. Right. But then, what if I change this to zero temperature? Then I need to use the zero temperature version of this correlation inequality, and you can prove that this T is replaced by like a low energy excitation. Like you can derive by Schwartz inequality that at zero temperature, if you try to derive similar inequality, this 2T is replaced by the excitation energy of your problem. Okay, this is the lowest energy excitation. Okay, and yeah, so so this quantity goes to magnetization M, which I want to be order 1, right? And this quantity in the denominator is a commutation relation between Hamiltonian charge operator K. So in the limit K goes to 0, they commute because this is symmetry, right? They commute. So you can expand it as K squared. So the inequality I have is something order 1, bounded as integral dk K squared over m times T for finite temperature and K squared dispersion relation times m at 0 temperature. Yeah, I only found I cited a paper who derived this inequality back in 1960. I forgot the name of that guy, but I cited the paper in my papers. Yeah, so now, because this is d minus 1 dk, and for the convergence of this this integral, so if d is smaller than 2, no SSB. And if the dispersion is k to some power z, then this is modified to d smaller than 2 minus z, no SSB. But in my case, this z is 2, so we are fine even in 1 dimension. Mm-hmm. Say that again. Okay. Thanks. Yeah, so previously I was saying, this Heisenberg model is really kind of special in the sense that it has SU2 symmetry, and that gives you quadratic dispersion relation. But what I needed in this discussion is only the dispersion part. I didn't have to have SU2 structure. But I just explaining how this theorem discussion is kind of escaped, right? In my model, the dispersion was soft. And I explained the reason why this is quadratic dispersion, right? Because this is frustration free. If it is gapless, my general discussion already kind of proves that this is a quadratic dispersion, because this is like spontaneous symmetry breaking example. So I have to have am I correct? Okay, anyway, like in this case, a K-squared dispersion is proven by a variation argument too. So yeah. No. The sign is the opposite. The Haldane gap case is you have positive sign. So like the system want to be anti-ferromagnetic. This is negative sign, so it want to be ferromagnetic. Yes. Great, thanks. Any other questions? Good. Yeah, good. Yeah, that is actually a good question. Like, so I think the Gosset and Fan type inequality if it is possible to extend to exponential decay, that's a very good question, and I think like someone has to do it. Like it's a open question. But the reason why I say I don't include exponential tail is that I can write down a tight binding Hamiltonian, which contains exponential decay in hopping, and which is actually a Chern insulator. Or like okay, so let me. So because I have only 30 minutes, I wanted to also talk about that a little bit. So maybe I quickly explain the free fermions. So the question I ask is, when I looked at this kind of Hamiltonian and asked when this Hamiltonian is frustration free. That's the question. Also, I have a separate question. Like we can always write this Hamiltonian into this form. So I find that this kind of tight binding Hamiltonian can always be written this way, and this like a matrix. So say I have a lattice site I here, and I have a hopping from L to K around this site I. So I need to kind of talk about how this kind of things decays as a function of I minus L or I minus K. They decay as a function of these lengths, but if I allow this Hamiltonian to decay exponentially, is this quantity, then even Chern insulator can be written this way. So this is a kind of tight binding Hamiltonian or with exponentially decaying tail in the hopping, and my ground state satisfies this condition. And this is Bengok Watanabe, PRB. Also, like if power law decay is possible, here I'm talking about decay exponentially, but power law. The simplest example of gapless tightening model is like I think nearest neighbor hopping model, right? And it has a cosine band. And I kind of decompose this Hamiltonian in a frustration-free form, allowing for longer range hopping. Then I found the power is actually cube. So if you allow for a hopping with this cubic decaying in distance, then you can even write rewrite this gapless model in frustration-free form. But this actually contradicts with what I have proven there, right? Because this is like a linear dispersive model. So the excitation is like 1 over L, in contrast to the 1 over L squared type behavior I was kind of stressing for frustration-free model in general. So that is why I'm saying the finite range assumption is important. It looks to me that once you include longer range hopping, the absence of Chern insulator type behavior is lost, and the 1 over L square type behavior is lost. So to me, to keep the general behavior of frustration-free properties, I think it is important to assume finite range hopping. And going back to this question, then okay, if this is the understanding for longer range hopping, then you can ask for a finite range hopping model. When is this Hamiltonian frustration-free? And what is the topological classification of this class of non-interacting Hamiltonian? And I don't have time to talk about that, but actually, you can just read Nick Reed paper, 2015, and he has a kind of tenfold way classification table for actually this class of Hamiltonian at the end. He has a discussion about what compactly supported one-year functions can do. And for example, frustration-free fermion can realize type chain, like a BD1 class, that is allowed, but Chern insulator is not possible, or any non-trivial topological insulator in dimension higher than 2, or higher than or equal to 2 is not possible, according to his result. So that is actually what I wanted to say. I have five more minutes. Okay. Oh, but this is the kind of end of the talk about the fermions. Do you want to hear more about this free fermion discussion, or can I go back to bosons? Okay, let me go back to bosonic discussions. Yeah. Okay. So the Nick Reed result is that for free fermion Hamiltonian E greater than or equal to 2 topological insulator impossible. The best you can do is like a 1D type chains and the stacking of it. That is for free fermions, frustration-free free fermions. So toric code is in topological order, and it's very non-trivial, and it is frustration-free. And the AKLT model is like a SPT model. It's the simplest example of SPT, and it is still frustration-free. And I think I need to also say, although I say topological insulators are impossible, people know that quantum spin Hall insulator. For quantum spin Hall insulator, there exists commuting projector type Hamiltonian. This is Chen Fang and other people in 2000 PLL. So this is possible because this is like an interacting frustration-free model. So, so the classification table for non-interacting and interacting case within frustration-free class are completely different. According to them, quantum speed-Hall insulator is possible if you are allowed to have interactions. But I'm saying maybe Chang insulator is still not possible, but I don't have a proof. But then like maybe Frank can explain to me. Even interactions are allowed. Yeah. It's gone. Yeah. So the symmetry-breaking order is protected by the Yes. Yes. So like you can introduce many parameters to the model, and you can pattern your this Hamiltonian in the direction of keeping frustration-free property. For example, like changing delta is such kind of things, right? Then it remains to be U1 symmetry breaking, but yeah, it can be either gapped or like a quasi long range order, yes. Yeah, maybe I should stop talking about new stuff and get questions or. Yeah. Yeah. I think this model is kind of. Yeah, I think like in general, frustration-free systems are usually like the phase boundary of different phases. You know, like phase 1 and phase 2, you have boundary, and sometimes on this boundary there's a special point which is kind of special frustration-free or something. So maybe you know if you increase the number of parameters and do that kind of calculation, you find it to be a boundary with different phases. Like say like Latimer point and phase and the symmetry breaking phase. Yeah, okay, but I don't know the full understanding of the phase diagram, or like more general. In general, you can ask, if the quantum frustration-free Hamiltonians have to be on the boundary or not. That I don't know. You want symmetry breaking? Yeah, but that okay. So that's actually what I wanted to talk from now, like mapping between classical subatomic model and the frustration-free model. But yeah, that time's up. So.
You have a model, some Hamiltonian. Do you have some kind of algorithm to check if it's frustration?
Oh yeah, that's a very good question. So if I'm allowed to assume translation symmetry, then if I have translation symmetry, then I don't have an index I here. So let me write like a prime GS. So each local Hamiltonian have an eigenvalue EGS, right? Then like a total Hamiltonian or total ground state is actually EGS prime times the number of sites, right? L. So what I usually do myself numerically is to diagonalize Hamiltonian for say length 2, 3, 5, 4, 5, and if it is really on the like a linear scaling, I kind of start suspecting that the model is translation free. If this is off the linear line, then I know that this decomposition is not possible, and so this is kind of necessary condition to be translation free. Right. So it depends on the range of this term, right? Yeah. If this range is upper bounded by 3, then like I need to start doing this from 3 or 4, right? But yeah, if you suspect the possibility of this kind of decomposition with longer and longer range hopping, then not sure if the good algorithm exists or not. But like it might be the case that even if the original Hamiltonian itself, I think like even if the original Hamiltonian itself has range 3, I think if you say it might be the case that translation-free decomposition might have longer range hopping. That is perfectly possible, right? Yeah. So if you allow for such kind of possibilities, then like this check may be not that useful. But, oh yeah. Yeah, like just look at the paper I draw here, like Sengoku and me last year in PRB. I think it's really like a undergrad level calculation, and I just decompose the Hamiltonian into like a translation form, but with allowing for parallel tail, and the calculations are all done exactly that part. So, but gaplessness implies parallel kind of things, kind of natural, right? Mm-hmm. Which assumption you say? I'm saying it doesn't contradict with the existence argument or of prohibiting the possibility of symmetry breaking in one dimension. Yeah, so I think that is this. So like after we wrote this paper, after I wrote this paper, like Adam Nafu wrote a kind of a field theory type discussion about this model, this type of model, and in his paper, I think he's talking about similar behavior, but without assuming translation-free assumption, and he's talking about like Goldstone direction, like this U1 fluctuation, and SZ, so like ferromagnet, you have a coset space which is sphere, right? Here I'm talking about, here I have only U1 symmetry. So so I have like this equator. This is Goldstone direction, and this direction is in general gapped. But he's tuning his model in such a way that this direction is also flat to some extent, like a quadratic term is absent. So the potential for this direction starts from quartic order. Then he say he can get the similar behavior, like a quadratic dispersion, and also it breaks U1 symmetry. So and this model is not translation free. So I think it is possible. Yeah. Yeah, but it depends on the meaning of the tuning. But so this is like usually this is like a kind of Higgs type direction, right? The conjugate variable, and usually it is gapped, but he is assuming that that potential vanishes. So he's tuning only one or two, very few number of parameters. That's not sure. It's a good question. Yeah, it's related to integration and many other questions. Yeah.
Any questions?
What is? Yeah, challenge related is not possible. Yeah, okay. That I don't have a concrete argument yet. That's like our kind of our conjecture. Also, like if challenge data exists, right? Like naturally, we expect the appearance of linearly dispersing edge mode, and that's kind of contradicts with what we have here, right? So, like many kind of reasonable argument, but it's not. But it also applies to edge modes as well. I'm just caring about the difference in energy, right? The ground state and the one above. This difference, what is it? Yeah, right. Yeah.
Since. Okay.
Sorry, I don't remember in the top of my head. So like when you compute collision function, right? Okay. Sorry, let me double check and maybe we can discuss later. Sorry about that. Yeah.
More questions? Okay, if not, let's thank Haruki once more.
Thank you so much.
Let's regather at 11:40.